talk to Python 3. My name is Ian Ward, and I'm an independent consultant. I've been doing most of my work these days in Python. I've got a lot of slides here, so I have to move fairly quickly. Basically, I'm first going to start to try to sell you a little bit, and then I'm going to spend most of my time talking about real code examples of what's going on. So basically, Python is a language that's designed to be readable. Now, usual people can disagree on what readable is, but there is at least the effort there. It's been around just a little bit longer than the Linux kernel, and it allows you to program a whole bunch of different styles of programming. It doesn't force you to take this style. So I quite like that. One of the ways it makes itself readable is by actually being fairly sparse. There's only 30 keywords. These are things that you absolutely cannot use for anything else except their official meaning in the language. And 130 built-ins, so just the symbols that come along as soon as you start the interpreter before you do anything. And that compares quite favorably to a lot of the languages where you've got this huge, huge library that you've got to deal with and understand. Another thing you'll find is that there's a lot less punctuation in Python when you're looking at the code compared to other languages, and that's something that I like. The documentation is also very easy to read. This is in part due to a very good tool called Sphinx and the restructured text format. So I used to put this presentation together. It's a very nice little format if you're looking for text markup. So the tools are very good. Pretty much everybody is using them, and you end up with a very uniform appearance in documentation across the community. There's also a concept of being Pythonic, and this means that there is not more than one way to do it. For most things, there is one way or a few ways that are considered the best way of actually going about doing things. And you can get a little bit of an idea about what that is with this little Easter egg. If you run the Python interpreter, you can import this to get the exam of Python. I like this little chart. This shows programming language popularity on Stack Overflow versus the number of projects on GitHub. When you're picking up, you can see Python is right up there with the other major languages. Now, this, of course, might be skewed more towards the open source world with GitHub. So let me get the big, contentious issue of right at the beginning. This code block here, the function called greet, begins and ends, it begins because of the colon and the indentation, but it ends when the indentation returns back to the level of the definition of the function. This is something that is weird at first and from most languages that you come to, but you do get used to it quite quickly, I find. And one important thing is that it doesn't actually apply in cases where you're inside a data structure or even inside parentheses. And so if you need to make a really long line or you need to put a whole bunch of data in your source code, you can pretty much do whatever you want as long as you're inside one of these characters. There's certainly other languages that do the same thing. It's called the offside rule, and you can see more about it there. Interestingly, it's also very similar to this quote by Knut in 1974. Python resembles this quote quite accurately. The other
too fast with the slides, Ian.
Oh, I'm sorry. You want to read the quote?
Okay.
It's okay. Are you done?
Yeah.
The big problem that comes up when you've got significant white space is that people disagree on what is white space. Is it space characters? Is it tab characters? How much is it? So sometime after I started using Python, this style guide for Python came in, and it was wrong. It wasn't the one that I chose, but I eventually got used to it. There is a big benefit to most code looking very similar when you're trying to read other people's code, when you're trying to switch from one library to another. It's true within projects. It's also true across languages. There are, I think it's the Go language has a single style guide for the whole language because they obviously find it to be a useful thing. And really the important thing to do is just configure your editor. Almost any editor can be configured so that when you press tab, you actually get 4 spaces. When it saves out the file, it saves it as spaces. When you press delete, it deletes 4 spaces back if you're at the beginning of the line. After that, there's really not much to complain about, in my opinion. The other thing to do when you're handling a huge pile of code that doesn't follow the style tagging is to use the tools that you're given. Along with Python, there's a re-indent script that can take some people's badly formatted code and fix it so that it looks the way it should. So let me talk about some of the things that I really like about Python. First of all, is the libraries that are available. There's tons of stuff in the standard library. You should look up this XKCD library, it's really funny. And there's also lots and lots of third-party libraries that will do almost anything you need. One thing that's really big is, Python's really big in the scientific community. NumPy and SciPy are libraries that are used to automatically, well, they give you data structures for really handling the scientific computing, dealing with large data. But they also automatically vectorize things. So when you just take these big arrays and you multiply them, the code will take care of actually making that fast on your hardware across your CPUs, across the hardware that you have. So this is a really nice tool. A little bit of what it looks like. An example of an interactive Python prompt and how you can just pop up stuff. I think the other big community in science for number crunching is around the R language and MATLAB. Stackless, something you might have heard of. It's a fairly fundamental modification to the Python language itself that gives you microthreads and channels. So these are things that let you handle lots and lots and lots of, say, connections, lots of things that are, lots of little actors that are doing different things and each routine without using real threads. It's been around for a very long time, but unfortunately it's probably never going to be merged into the main, into Python itself because it changes it too fundamentally, it changes the language to a fundamental level. It changes the way other things behave. But it works really, really well. In particular for EVE Online. If you've heard of this, this is a massively multiplayer online game, and they've actually managed, apparently, to get one server running an interpreted language supporting 30,000 clients at a time. That's pretty cool. Another big library that you might come across in Python is Twisted. This is the sort of de facto event-driven framework for doing network stuff. It requires programming in a little bit different style. It takes a little while to get used to, but the best part of it is it comes with SSH, client and server. It comes with mail clients and server. It comes with web. It comes with all this stuff. And so hooking this stuff up to do interesting things is a whole lot easier than, say, configuring a whole bunch of discrete services and trying to set up communication between them. So you can do some very interesting stuff. Oh, it's very good for that. If you want to manage lots of connections and you want to deal with lots of threads. Plus, it has implementation for lots of standard protocols, so there's a lot less to write. The main thing is that you are working in an event-driven design. So you're writing code that is these tiny little functions, and that just goes to the twisted reactor and says, okay, please go through this stuff, and here's a bunch of other functions that I want you to call back if this, that, or the other happens. So that handles or that takes the blocking out of your code, but also can make your code quite hard to read if you're not used to programming in that style. But it does do a very good job. The way I'm making most of my time these days right now is with web stuff, and in particular Django. Django is a very large, very it's well-established now web framework that takes inspiration largely from Ruby on Rails. And it has all of the benefits and drawbacks of being a large established framework. I quite like it. So I have to group the actual development process of Python in here as one of the killer features because I find it works quite well. There is a benevolent dictator for life, Guido Dan Awesome, who does eventually have the final say on everything, but all the development does happen in the open and public analysts. And for any fundamental, for any core changes to the language, they've implemented a process called Python enhancement proposals. This puts the onus on the person that has the wonderful idea, and there are lots of people that have ideas about just the perfect way to make the language a little bit better. It makes them do the research, find all of the related suggestions, gather it all together in one document, put it in one place, so that people on mailing lists have a point to argue, either for or against. So this is their chance to make the case. It's a process that works very well. It's influenced other languages to take it on. And interestingly, some of the suggestions, even from Guido, that have gone through this process, he has later rejected. After he's had the proper criticism. So it obviously works quite well. So my talk is on Python 3. If you haven't been following development, Python 3 started out being called Python 3000 as sort of a joking reference to, well, these are all of the changes that we'll do sometime so far in the future we can't possibly fathom it because it's going to break absolutely everything. Eventually that time became the present, I guess, where the weight of those changes got to the point where the developers decided that there's so much of the stuff that we don't like about the language, but our hands are tied. We just can't change it because it's going to break code. It must be better to do this once. To break things, do a non-backwards compatible conversion, fix the really bad things that have been bothering us, and that hit every new user that comes to the language. And the payoff will eventually be worth it, because the number of new users coming to the language will eventually outweigh all the people that are upset by the changes. So fortunately, part of the plan provides tools that do actually help with the migration. And they are by no means complete, but they do really help you actually. It is possible to manage code that works across versions. You just have to be careful. So the transition is still underway, and it was always planned as a 5-year, at least, transition for the majority of people to move over to Python 3. We're part of the way into that right now. And through this whole time, all of the new development of the language has always been in Python 3 first, with a handful of features that made sense being brought back into earlier versions of Python, or late versions of Python 2, I should say. Because such a major change was being undertaken, there was also an unusual step of a moratorium was declared on any fundamental change to the language for 2 years from the point when Python 3 was released. Because there was always, on the mailing list, floods of people that had ideas about things, this little pet project, that pet project. So they just said, okay, stop it. Help us clean up the standard library, fix the things that need to get fixed in Python 3 so that we can get this into the hands of users. That just expired recently, and interestingly, it hasn't actually resulted in a huge flood of similar requests. It's actually been quite quiet. There's been a few changes that people have expected, but the language change, rate of change has actually slowed down quite a bit. So whether you can use Python 3 right now is largely determined by what part of Python you're using. And these are some large projects that have not added support for Python 3 yet. So big ones there, of course, Twisted Django. The Python imaging library doesn't have support yet. Lots of people are using that. And none of the alternative implementations, which we're going to talk about right now. One of the ways that, or part of the active communities around Python are actually in being able to run Python on things that it wasn't originally designed to. In particular, .NET and the JVM. These are very popular for people that already have a big infrastructure, people that are that are heavily invested into these technologies, and they're very actively developed and used. It's to the point where you can actually take a Django project, wrap it up in a WAR file with Python, hand it off to your network guy, and he will never know that it wasn't written in Java. So it's very nice for stuff like that. It also has full use of all the facilities, so if you need to use the proprietary bits or the peculiar bits in each of those, you can do that. If you need Python to go faster, there's projects Shedskin and Cython. They're all about sort of partially compiling Python code into C, usually with some script types. But the really, really exciting, for me anyway, project right now is, as far as alternative implementations, is PyPy. This is Python implemented in Python itself. And when these guys came around, they said, hey, we're going to write Python in Python, and it's going to be faster. And so it's like, haha, yeah, okay, you go do your thing. Well, they never went away. And so 8 years later, they actually are faster by something like 3.5 times. And And they do this by jitting the Python code. They have a tracing JIT, a very lightweight tracing that follows the execution, finds the paths that are heavily used, and after a path gets hit 100 times or something like that, then it'll actually generate the machine code for that complete path with any kind of deviation from that path, causing a track back out into the Python interpreter where it starts interpreting again. And it just keeps doing that, and then common paths that are taken end up getting jitted as well. But it's not just for Python. They've actually also written sort of proof of concept front ends for other languages. So you can use this on JavaScript, on Prolog, on Smalltalk, at least in a basic way. And there's a stackless mode, so you can use it as though you were running stackless, that version of Python. And you can compile it against .NET or the JVM. So they've really sort of gone all out. They kind of want to be all things, just better Python for everybody. It's a very interesting project.
I understood stackless was another implementation.
Stackless is a modification of the core of Python in the way that your code might get preempted by some other thread. I'm going to use the wrong term, so I don't use it myself. But essentially, control flow could jump all around depending on things that are not really like the regular Python language.
What I mean is, it's another interpreter. It's another interpreter.
Yeah, I guess it's like a fork. It's a fork of the C Python interpreter.
What I didn't understand is what you mean by Python 3 supports stackless.
Oh, so the stackless fork has maintained has. Oh, let's see here. Does stackless fork work? I actually can't remember what I had. Yes. So the fork has actually followed C Python all the way into version 3. So you can get stackless for Python 3.
So it's been merged into Python 3?
It hasn't been merged into Python 3. It's still available, so you still get all of the Python 3 language stuff, all that good stuff. But you also get the stackless semantics where instead of writing tiny little functions that then hand off a bunch of other functions to you, you can sort of pretend as though you're running and blocking, but you're not actually blocking. Execution is actually jumping somewhere else. So, this is the chart from the PyPy site, and you can see, you might be familiar with the Unlabeled Swallow project that was in Google for some time. That was another alternative implementation, but that eventually sort of stopped, or maybe it's just resting. But one of the best parts that came out of it was actually a very, very good suite of benchmarks that test real-world sorts of things, running web servers, doing database work. That is actually a fair test, because for a long time we didn't have very good benchmarks. These are those benchmarks against PyPy. So now I'm going to get into the code. Strings in Python are going to be different than you might be used to. They are immutable. So once you create them, they're safe. They can be passed around and used other places. So they're actually a little bit like symbols if you're used to Ruby, and they're used that way because for short strings, if you actually execute this code, those two strings not only would be read-only, but they would actually be the exact same string. Because anytime there's a short string, it gets interned and then looked up. Anytime you create another short string, if it already exists, it just gives you another reference to that old one. Also, the coding doesn't matter in Python. Double quote, single quote doesn't affect anything. You can use escaping like you might be used to in C. Works just the same. But the big difference with strings, though, is that in Python 2, a string was an 8-bit binary value. Whereas in Python 3, this string declared in that same way is now Unicode. So each of those characters represents a Unicode code point, not 8 bits of data. That's one of the trickiest things to get around when you're upgrading. In Python 3 and in later versions of Python, you can also mark binary data. So if you actually really want an 8-bit value, you prefix with a B. And in old versions of Python, Unicode used to have a U as a prefix. Yes?
Will Python share substrings of other strings?
Will it
share substrings of other strings?
I believe there are classes that do something like that if you need them, but by default it'll create anyone if you do that. This is handy for people on lesser operating systems and for people that deal with a lot of regular expressions. You prefix with an R to get the raw string, so those backslashes are not escaped in there, they're actually in the string. So this is what some of the standard operations look like. There's a length built in for length. You can access from the end of a string with -1. It'll counts the other way, and then you're just asking about a slice, like a substring. You can do that with the sort of array notation with a colon. That gives you characters between 6 and 9. But you also notice that in is an operator that can be used as a substring match. So here it's finding the HE characters in the string. Lists in Python are implemented as arrays, and they are mutable. So they're the most sort of they're the workhorse data structure just for turning through stuff, changing it, adding things. It has an average O1 append, so you can just keep appending. You don't need to worry about the performance of that typically. And it has a lot of operations that look sort of like strings, except here you're operating on items in the list. So you're getting back the individual strings for the list. It was convenient for me to create this list by just splitting the string, which by default does on spaces. That gives me that list of 4 elements. And now you'll see this in operator no longer does substring matches because it's operating on a list. So that would have to be an exact match in order for that particular code to be true. Tuples you'll see as well. You can essentially just think of them as immutable lists. They're often used for passing data around, so you know that the function that you're passing it to won't change the value, but you'll see them in a lot of other cases. So here's a little bit more interesting function. I've got some parameters now. Some of them are optional. They're optional by giving them the default value if they're not given. There's a block in here, again, just determined by where the indentation goes. And you'll notice I'm using the if statement on the variable without comparing it to something. This is very much in the duck typing style. You're allowing the object to declare whether it's to be considered true. And truth in Python is really basically false, none, and 0 are all not truthy. And pretty much anything that's empty is not truthy, and almost everything else is considered to be true. So you will commonly just say if variable name that I'm interested in, colon, do some stuff. And you can kind of read it like if there's something there, if there's something worth processing. So the other really big change that's very visible between Python 2 and Python 3 is that print used to be a statement in Python 2. So you would say print like this, print a string. You can say print string, comma, another string, and it will automatically stick a space in between those two. And if you put another comma at the end of that, instead of putting a new line, it puts another space and lets you print again. Okay, so it's originally designed as a teaching language. I can kind of understand where they're going with that. But it gets a lot worse. They realized, oh wait a minute, we need a way to direct these print things to other files. Well, let's just borrow this thing from C++, I guess, that totally blends in with Python and doesn't stick out in any way at all. Terrible. But it does get worse. On the other side, the default input, or rather the input function that comes with Python, actually executes, evaluates what's passed into it. So every new user that comes along to Python and wants to make a simple program just reaches for the input, and they think, oh, this is great. But that's just so unbelievably wrong. I mean, it's so bad that I've seen tutorials on the internet that have suggested that, well, you use raw input if you want a number, and you use input if you want a number, and you use raw input if you want a string. A raw input is the input that it should have always been. You should have always gotten a string from a function called input from the user, and then you should have just dealt with it in a safe way. But this is, again, one of those things that you can't fix without breaking people's code, but it really should be fixed because everybody gets new tricks over it. This is the solution for the print statement. Print is no longer a keyword in Python 3. It's just a regular built-in function. And like a function, you could override it. You could have some other function called print that you could call instead. And hidden, or the automatic separators between things, you can now specify. So I can say, I want my separator to be a space, or I could want it to be something else, and then we'll put a space. And I want my ending character to be a space, or a new line, or of course we close new line. But there it is, it's like a normal function. That's great. And also for the file, you can just specify it as an optional parameter. It looks a lot.
It's still a keyword.
It's no longer a keyword. It's just a normal function. Go over this fairly quickly. Lots of different number types in Python. The biggest difference that you'll see is that integers used to be divided into normal integers that would fit into whatever machine registry you have, and long integers that are arbitrarily sized integer values. And the representation of long integers used to have an L stuck on the end of it. There's no distinction there anymore. Integers are just integers. They're all arbitrary sized long integers. And this change is one thing that taught me that I didn't realize this was actually, they tried to fix this back in the really old versions of Python 2. And that is, if you divide two integers in Python, being a good C-inspired language, you got back an integer. That makes sense, right? Well, apparently for a lot of users, it really gets them messed up. So the decision is division. If it's going to have a remainder, then you give them a float instead. If you want floor division, there's an operator for that. It's the 2 slashes. So that's the one you're supposed to use. You'll find dictionaries all over the place, and they're sort of a fundamental data structure. They're the hash table of Python. It's nice to know there's also a fast path code in there for use with strings, which is the most common way these are used. But you can use any kind of immutable thing as the key in a dictionary. So they look sort of like the other collections I was showing you, except that of course the keys are the keys of the dictionary when you're accessing them, when you're setting them. And when you're testing for membership, you're testing for membership with the keys, and likewise with the in or with the operator.
Why is 3 in default?
Because 3 is a value, and when you're checking for membership in a dictionary, you're looking at the keys, not the values, because that's what's hashed. So that operation will be equal 1, right? And if you really want to check the values, then you have to actually loop over them. There is this, you can call dictionary like a function and use this keyword style parameter too. Some people, you may find that in code, so just a heads up. Everybody here should be used to C, so string formatting should look really familiar. Basically, Python kind of took the printf style and said, well, if you take a string, use a modulus operator, and put a couple of values on the other end, you get basically an sprintf. That turns it into a string formatted the way you would expect it from C. They extended that though, and this one is actually really nice for localization. If you've got strings that, you've got different languages that might require swapping the orders of variables, you can also, instead of a tuple, you can use a dictionary to pass into this format. And then you specify the key value in parentheses as part of the format string. For some reason, they went even further than that. Well, I can kind of understand it. There's yet another way of formatting strings in Python. I think somebody had intended to actually make this the standard way of formatting strings, but the percent formatting is just too ingrained that there's no way to get rid of it at this point. However, you can call format on a string, and this has a different syntax. I think the main argument for this was that people that aren't used to C, yes, they exist, I guess, they were always forgetting to put the character at the end of these format strings. So they put percent in the thing that they wanted, but they forget to say S or D or whatever. So let's make one that just uses curly brackets with the name. We can pass in values, and then it'll work the way they expected. And for some reason, they added something like printf, but not quite. They used greater than, less than signs instead of just minus or not having a minus. I guess that let them also add that you can use the tilde if you want centered strings, which is of questionable value in my judgment, but there it is. This is where they can actually get a little bit more useful. Some languages, like Ruby in particular, I think you can execute whatever arbitrary code within strings, and have it replace the value in line. So this doesn't let you go that far, but it does let you dig into dictionaries or objects with attributes. So this will actually go into, so S is passed in as the thing that's being formatted, but then I'm going to reach in and grab the value of product and put that into there. And here I'm going to go 2 steps. I'm going to grab the value of stores, and then I'm going to get the first item in that list that's contained in stores. So you can traverse, relatively complicated data structures all within your string formatting, if that makes you happy. So if you've been paying attention, you'll notice that some of these functions I've been calling, I couldn't have possibly known what the parameters were going to be ahead of time. So this is the way that Python handles variable optional parameters or a variable number of ordered parameters. And this is with the so-called strat operator, where any parameters that are listed at the beginning without giving the names go into args as a tuple. And any that are given as keyword arguments, so that you put the name at the beginning here, end up in a dictionary. And from there, you can do whatever you want with it. So here I just printed it out. You can see what happens with a regular function when you're past that stuff. The scoping language is a little bit different than you might be used to. First, you look at the local, something that's defined in the function. Then you look at in closing functions within functions. You might not be used to. Then you look at the global scope, and then finally into the built-ins. But the important thing is where things are defined. So, where things are assigned. So the top one here looks like a normal assignment statement, but in Python, like a lot of dynamic languages, these things are also assignment statements. An import is actually just assigning basically the contents of a module to a variable, in this case called twisted. Defining a function is just us creating a variable called that function name with the function body, essentially. And same thing with the class. So where you actually have that is where Python looks and tries to figure out which one is going to be used. And if you need to choose a different scope, particularly if you've got nested functions and things, the way that you override it is with these keywords. So I'm almost to the interesting stuff here. I'm going to start with a closure, which is common in a lot of dynamic languages. It's a basic concept that you couldn't just go over carefully at least once. What a closure is basically code that wraps up some data and then is passed around to something else to then get used. And so the way you do it in Python is usually by defining a function within another function. So when you call this function, you're passing in a value for v. And then inside of defining a function that uses that value v. And when I return the function itself, this new function that I created inside my function, it carries along that value v so that whoever calls that function still has a reference to it. Make sense? One of the things that trips up people here is the difference in Python between statements and expressions. Statements cannot go inside other statements in Python. That has a happy side effect of making it impossible to accidentally do an assignment within an if statement. The common case of forgetting an equal sign there. But it also sort of forces people to make their code read down the screen instead of all get scrunched up into one line, which is a nice benefit too. But I just want to cover off a couple of the things here while I'm looking at this. This comparison doesn't do what a C programmer thinks it does. It does what a math person thinks it does. Actually, it will only return true if x is actually between 9 and 13. And this is Python's ternary operator. It's the wrong order if you're used to C. The true value that gets returned is over here, the condition, and then the false value is here.
And why?
Why? The mailing lists on this are exciting. I mean, the back and forth, the proposals for how to add this, and sort of the undefinable arguments about what actually looks Pythonic. It was eventually decided that reusing the keywords that they already have in this way was the thing that looked the least unlike the rest of the language. So, and that last one there is a lambda statement, which is much derided in people that are used to functional languages, because it's a lambda expression. Because it's an expression, it's not a statement. You can't put statements inside it, so the code you can actually put in there is very limited. Lambda is an anonymous function. You're just so this returns a thing, a function of one parameter that will square that parameter and return it. I kind of like lambdas the way they are, because if I want something more complicated, it's sort of nice to define it as a separate function and give it a name anyway. But there you go. So basic while loop. This is actually it's really Fibonacci, but I just wanted to show you here assignment. You can assign multiple values in one statement. That's okay. Two different variables are being assigned the same value, and you can also assign multiple values to different things. So here, parents is being assigned to babies, and babies is being assigned to parents plus babies. And the while loop, well, nobody would expect it. It exits when babies is less than 100. Going further than that, though, in general, so that was the top assignment you saw at the top. The third example here, you can actually assign to nested tuples, and we'll unpack things. So A gets assigned to 1, B gets assigned to 2, and C gets assigned to the tuple containing 3 and 4. Better than that, Python 3 took it even further. You can use the splat operator inside tuple unpacking. A gets 1 and 2, and B gets 3. A gets 1 and 2 here again, B gets 3, and C gets 4 and 5. You either like it or you don't. I mean, it's a more basic version of parameter matching that you get in some other fancy languages. So you can do some things that are handy if you're dealing with certain types of nested data structures in a very concise way, because this is the way of doing the same thing in Python 2, which is, I would say, harder to read. So still on basic stuff here, a for loop will take anything that can be any kind of sequence, anything that can be iterated over, and run the block of code with the variable assigned to each one. There's no automatic counter, so if you need a counter, in this case I've just created a new variable and I've incremented it myself. And that's one common idiom that you will see, especially with new Python coders. But the better way is to actually use enumerate, because it's a fairly common thing to want an index as well as a value when you're looping through things. But there's something going on here. So, well, first of all, notice that we've got the assignment to two values happening at the same time in a for statement. So that works, and tuple unpacking and all other magic stuff works within the for statements. But if I have a look at my interactive interpreter, what this enumerate thing is, it just gives me this thing. It's an enumerate object. Well, that's not very helpful. But I can convert it to a list, and I get what I expect. So I expect that I'm looping over values of index and one of the strings from this, because that's what I would need in order to unpack the way that I want it. So, what is going on there? Let's have a look at some of the interesting parts of the language. I'm going to start on generator expressions. So this is a pretend shopping cart. I've got quantities, and I've got prices, and I'm calculating, it looks like I'm calculating the sort of totals for each of these line items. This is a new way of showing for and in. This is not a statement, this is an expression. So you kind of have to read it right to left. So you read, for F in purchases, so this is the fruit in this purchase dictionary, I'm going to multiply the price by the quantity. But this, for in, within parentheses, is actually a generator expression that doesn't get executed until it has to. So the place that it gets executed is actually on the next line here where we're calculating the sum. Maybe it's not that exciting in this case, but if you've got tons and tons of data, this saves you from all the intermediate storage, right? And you could be doing something more less trivial than just multiplying two numbers, right? So it's a handy way of expressing something that can be done across the sequence, and then making it lazy so that it happens later when you actually have to do it, not right away. Is that okay so far?
Can you just explain what it does with purchase there? Because it looks like you want to be iterating over the keys, not the entire set there. So does it implicitly apply keys there?
Okay, so yes, no, that's a very good question. So when you're looping over a dictionary, you're actually giving the keys. So that's like when you're testing for membership in a dictionary, you're just checking the keys. And when you're accessing it, of course, you're using the keys. So this syntax gives you the keys to loop over. There's another syntax that you can use to get the key and value at the same time, but I want to make the example simple.
Yeah, it's sort of amazing.
You might have seen these before, and actually there was a survey done of Python developers as to what their favorite language feature was. And number one by far was this thing called list comprehensions, which is essentially the exact same thing as a generator, except instead of the cool thing, which is that it's lazy and doesn't happen later, it just gets stuck in a list that happens right away. And the syntactical sugar for that is you just use square brackets instead of round brackets, and then you immediately have a list that you can play with. So you'll see this all over code where it's just simple processing up where you want to stick the value in another list.
So what was the type of putting in round parentheses then?
This is a generator expression. So that, if you looked at it, it would just say generator expression at blah, 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 blah. It's a bunch of code that hasn't yet been executed. Whereas the other one gives you a real, honest-to-goodness list.
So when does the code actually get executed for the generator expression?
When it's required. So once you pass it to something that needs to start working on it.
So in the previous example, it would be
When you did the sum.
when you did the sum?
Exactly. So the intermediate values are never stored. They're just being created as the sum function needs them to have them.
So it gives you back what, a code object?
Essentially, yeah, it gives you an object that it can be iterated over. But that's not flexible enough. The next step in generators is generator functions. And generator functions introduce the yield keyword here, and that's the clue that there's something different going on here, and that's the only indication. This looks kind of like a Fibonacci function that would just loop forever. But what the yield statement says is run to this point and then pop that value out. And this is the next value in this generator. And then when you need another value, execution continues from that point until it hits another yield, or when it exits the function, you're done. Those are all of your values. So the fact that this would run forever doesn't matter because I'm only calling it until I get the value that I want, and then I'm stopping. Does that make sense? So into my loop, when I create this object, again, I've got one of these generator things, and when I ask for the first one, it executes until it gets to the yield statement. Gives me that value, which I print. Right? Then I come back to my loop, ask for another one, and then it continues up here, gives me another one, and then the next value comes in. Is that good?
It's kind of like a coroutine.
Yes, very limited coroutine. So these can also take arguments. So if I wanted that limit for when I actually stop to be inside the generator, to be part of it that I created, I could just include an argument to my Fibonacci generator function, and it can stop for itself by just returning out of the function. And then my code that uses it gets really simple. But it's the exact same logic. It's still just generating them as requested by the code that's running through that generator.
What happens when you mix yield and return? I've never seen it.
Return basically says that there are no more elements. Internally, it's a stop iterator exception, but that's the way of saying it's done. It's the same as if you drop off the function, right? Okay, that's not interesting enough. What else can we do with these things? Let's try putting a generator inside another generator. Or actually, in this case, I'm going to use a generator as a filter of another generator, and then string them together so that as I turn the crank and I start asking for values from that filter, it asks for values from the next generator and then passes them through. So this is a doublet. This is a normal function here, actually. A doublet just returns a generator expression that gives me double of any kind of values that come out of the sequence. And in my actual code, I'm going to wrap that filter around my generator and just start looping. And so now we've actually got two of these generators that are cranking at the same time for each thing that I'm doing. They're going through doing their thing, popping the values out, and then giving me the end result of this. So it's a trivial example. I mean, a more real-world example, you'd be doing more interesting things in each of these, but the idea is that you're abstracting the complexities of the particular processing step that needs to be done into these generators, and then you can hand off that in a way like this, and then just treat them as though they were all sitting there in memory, and you can just loop over them.
So in this case, you wouldn't actually need the for loop in doublet, right? Because you're only dealing with one.
There's only
like in this specific example.
Well, this isn't a for loop. That's a generator expression.
Well, no, but I mean, it would, like you only need to deal with one argument.
I'm not calling a function on every argument that is passed. Here, let me see if I can trace this. Maybe that'll help to make it more sense.
It looks like you're calling Fibonacci, n times or 14 times, or yeah, 14 times.
I'm looping over values that are returned by the thing that doublet returns to me, right?
Okay.
Doublet is returned me a generator that is operating on the Fibonacci that I passed in, which is another generator.
How many times does doublet get called? Does doublet get called 6 times or once?
It would get called once, because all it's doing is returning a generator to.
But don't you have to be calling in the loop multiple times?
The generator
and each time?
The generator gets asked for 6 values.
But you have to run the generator multiple times. Like each time you're evaluating n, the output of the generator. So don't you have to call the generator once for each output value?
Well, sort of. I'm calling it to ask it for another value.
Right.
But the generator is an object that can be treated like a sequence, right?
But doesn't that mean that doublet will also get called once per iteration?
No, doublet's only called once. Any code that's in on this side of a for loop is code that's used to generate the thing that you're going to be looping over.
Okay, but how do you then know when n has exceeded 14 if you're not evaluating the output of doublet each time?
It's not the output of doublet, it's the output of the generator that doublet returned to me.
So the first time you come to this, the generator expression gets calculated, and after that it just gets called?
It's just an object. Like this is just a fancy way of saying I'm making a new object that will double things that come out of another thing that's passed into it. Sorry if this example is not as enlightening as I hoped.
So, what is the value of sequence initial?
The value of sequence is initialized to what's returned by Fibonacci, which is that other generator we were talking about. The one that would run
Also,
forever.
one piece is missing.
Can you please roll back a bit to the Fibonacci? I forgot
sure.
it. I'm sorry.
Here's Fibonacci.
Just incredible thing.
So this is a thing that I could ask for values forever. It'll just keep giving me numbers.
Reset your generator.
I'll get it to that.
But then it just gets called once in your for.
Well, it's a little bit weird because it's not a normal function. When you call it, what you get back is a generator, which is code that has yet to be executed. So when you look at it like a function, it's kind of confusing that way. So it is only called once. But the result of calling this is a new object that sort of contains all of that code that needs to be run in order to give you the values that you're going to ask for.
I guess because
I got a question. You said originally that this was a teaching language? It seems like we're using both riddles at this point.
I'm up here having fun.
Good, as long as you're not using symbols.
Anyway, it's not. I might have failed at clarifying something that I thought was an interesting language concept. But I'm happy to take more questions later if somebody wants to work with me to unravel some of this stuff if they find it interesting too. So, getting back to the more fundamental of what these things are, it's a concept called iterator set, which is, again, it's just an object that you can call next on. So here's my earlier generator that does actually end somewhere. At the interactive prompt, I can call next on it, it'll give me a value. I call next on it, give me another value. I call next on it, gives me a different value because, of course, the state in there is being modified as I'm calling it. And eventually, when I hit the end, I get a stop iteration. So somebody was asking about resetting. I'm a little bit worried I shouldn't go into this. I don't want to get into the code. Okay, so, well, let's say we've got some monstrous amount of data that's separated by a bunch of monstrous amount of text data that's separated by colons. And we don't want to take that huge string, split it on colons, get a massive, massive list to then process each item. We just want to start looking at each item one at a time in a way that's easy to code, or sort of easy to use. This is maybe a little bit confusing. But this is a generator that will give us one of these blocks at a time. So it'll give us the single and then the number 248. Well, it'll give us the string 248, and so on. So this is the sort of limited feature of Python to actually have something a lot more like coroutines, because you can actually have data go back and forth with these things. This is a modification of the last code that I showed you, but the significant change. Don't worry about the specifics of the splitting the string at the right spot around the colons and stuff. That's not interesting. But this part here, my yield statement is being assigned to a value. What that means is that not only can I just ask for another value from this thing, I can pass data in that can influence what it does for its next value that it gives me. So in this way, we can use the language to essentially control this, like, control your generators like they're little robots. And you can give it a little command set. You can say, okay, we'll do this, and then do that, and then do the other thing, and it'll keep feeding stuff back to you. So in the cases where it's not enough just to have something that will run the same code again and again, you can actually feed data back into these things. This is what that looks like. So if I just call next on it, like a normal generator, I'll just start getting these things, single and 248 and in between. But then if I call send, I can put a value in there that changes the way that it behaves. In this case, the behavior is I'm asking it to go backwards in my string of things instead of forwards. And here it gives me the value before instead of after. And so this is sort of my attempt at a simple example of a generator that goes off and does its stuff. It's sort of in the middle of its code and sitting and waiting, and then you can poke it with another command and it'll go do something different than it would have just done if you just let it run all by itself. Yep. So this find stuff here in the particular things is all just about giving strings that are actually in between the colons.
Send is not another function.
Send is not in here. Send is another way of talking to this generator. This whole thing is giving us back an object. So instead of saying next, I can say send. Actually, exactly the same as calling next on it. I can say send none, which is sort of the nothing default value.
And the behavior can be overloaded, obviously.
Yeah. I mean, you're basically defining an interface for this little robot that can go off and do things with its own state. Instead of having state in a class serialized somewhere, and then every time you come back into the code, you have to come back in the beginning. You can have code that stops in the middle and then keeps going.
So find moves forward and find moves backward.
Mm-hmm. Okay.
Is there any way to do this so you can feed data and rewind on the first invocation of
No. You'll actually get an error if you try to send to a generator before if you try to send anything to a generator before asking for the first value. So no, you have to ask for it has to give you a value before you can give it any control. That's a quirk of the language design. Let's take a little break. I like generators, but exception handling. So we saw an exception there, and some of you might be surprised by the fact that And a stop iteration exception was what Python uses to say, this is done, you're not getting any more data, that's it. Because in most other languages, exceptions are very expensive things. You have to create all these data structures, you've got to be all careful about what's going on, and then carefully tear it all down where you're landing to deal with it. That's not the case in Python. Exceptions are actually very fast, and they are commonly used as a first-class control structure. In fact, in PyPy, if your very commonly executed code path happens to create an exception, which involves creating this, like storing a stack frame, creating a bunch of variables and whatnot, that can actually be completely optimized out. Raising an exception and ending up in a different function could be 0 operations on the actual result legit. But this is what it looks like when you're handling exceptions. And this is a working example of Python code that will add a bunch of numbers that you put on the command line. So, okay, I couldn't get away from my generator. So here's a generator that converts to an integer each argument. That's my slice notation because I don't want the command, the first parameter is the command that I'm executing. And then I'm going to sum them and I'm going to calculate a total. So the clauses here, you always want to accept and tell which type of exception you want. If this integer fails, if this integer conversion fails, the control flow will end up on this print statement, and I'll tell, say, oh, bad user, you didn't give me what I wanted. Else might stick out as being kind of funny. Python tends to stick else on a lot of control structures that you wouldn't see in other languages. While blocks, or blocks, like else blocks on them. I like them, but the main point for this is I can get the exact same result by taking this print statement and sticking it underneath total there, and the program will work just fine. But the subtle difference is that I'm only interested in value errors that happen in this first line. So else gives me a place that I will come out to if no exception is raised. So this try except could be try except else, if you want, with a block of stuff that gets run when no exceptions were run. And in older versions of Python, try finally was actually a separate thing, but it became really, really common to put a try finally around the try except, and you have all this nesting. So now you can put finally on the end of these big long except blocks. So that print statement only gets run if there's an error. This print statement gets run when there's no error, and this print statement will always get run.
Why not put the line under the else after the finally print, like other languages?
The line after the...
Take away the indentation of the print.
If I take away this indentation of the print, then that will print even when there's an error. And I don't actually have a valid sum.
Raise that finally, and if it's going to be run no matter what, what's the difference? You could just take out the finally clause.
Oh yeah. The finally case in here isn't necessary. The case where you would use that is if you've got some control in there that might leave the function. Like if I could have a return statement or something up in here, and this code would still get run. You're absolutely right. In this case, it's not required.
What happens if there are no arguments? You just leave one?
Oh, no arguments. You'll end up with an empty list here, and then this won't loop. There's nothing there, so this ends up being an empty list. Some of an empty list is arbitrarily defined as 0, and so it'll just print 0. If you wanted to check for that condition where there was no extra arguments, you'd have to actually do that. I couldn't think of a thought of that. There isn't a all-in-one line way of doing that. You have to actually say, if the length of this is less than what I expected. Okay. So here's a finding that does actually do something. And oh look, I'm doing a generator again. Sorry guys. So actually, one of the hardest things about getting generators into the language was the developers couldn't figure out how to make finally work properly, or it was a very, very large challenge. Because finally is very important for things like freeing external resources, right? Your file handles, your database cursor, whatever. But if generator functions are like normal functions, then you should also be able to have cleanup in generator functions. So just to show you that yes, it does actually work, and yes, it is weird. If you go into a try finally block inside a generator function, you still get the guarantee of the finally code getting run, even if that generator would never, exit on its own. So this would just, of course, would just keep giving you ones. But so what happens is that this object just goes out of scope eventually, and when it goes out of scope, it's remembered that it has some code that it has to run, and that's when the code gets run. So I'm creating a generator, calling it a couple times to show this it does work, and then when I leave the function, the finally code gets run. Okay? But better than finally. The big problem with finally actually is that it sticks the code in the wrong place, right? You open a file, or you start using a cursor up at the top, and then somewhere way down at the bottom of the code that's finished using it, you have to remember to stick that file in, and you have to remember to run the right code to clean it up. So that bit of code at the top and that bit of code at the bottom are tightly linked, but they can't be together. To solve that, there's a thing called context managers and the with keyword. So the with keyword here, you can pass something that knows how to be a context manager, which is basically something that knows how to open itself and how to close itself when you're done. And then you can run code in the middle. This is something that I don't use enough because I have to use old versions of Python, but it's a really nice thing to make sure that you clean up after yourself. So if you're using one of the locks in language, you can just say with lock, do some stuff. Very nice. Can't get it wrong. I like that. Similar sort of argument applies to function decorators. This might not be something that you do every day, but there is in dynamic languages, it's common to take a function and then modify its behavior in some standard way. And take many functions and modify their behavior in a common way. Change the way the values are passed in, maybe verify them or something. This code here does that. It's a function that takes a function, and then it returns a new function that does something first, then calls the function with whatever was passed in, and then it does something else before it exits. So this is a function that modifies another function. And the old way of applying that to my say hello function would be to just put say hello equals show enter and exit, open parentheses, say hello, close parentheses. Which is, well, it's a lot of repeating yourself. You gotta say have the name of the variable in there 3 times. And if this function is not trivial, if it's more than a string long, you're never gonna see that you've reassigned that name to something else, that you've modified it somehow. So that's the argument for this operator, and you're supposed to remember it as kind of meaning this function wraps that other function. And a lot of things, I mean Django in particular uses a lot of this. You'll have common ways you want to modify a function, and you just stick them on as decorators above the function. But otherwise, it's exactly the same as just assigning to the same name, the function being passed into this other function.
Just a question. Is it possible to create something like a C, I would say, macro, underline function name, underline in here, in order to understand which function was called?
Oh, that's actually a really, really good point. There's a module that comes with Python called, it's not functools, it's another one. I'll remember later on, but there's so the fundamental point here is that functions do actually know what their own name is. Like so say hello, I can find out what its name is, like you said, under name. But by modifying it, by wrapping it in this other function, I get this object. If I ask this new object, the new say hello, will actually think that the name function is inner, right? Because that was returned and that's what was replaced. So there's a utility for creating these function decorators that fixes up the name, fixes up function signature, so all of the sort of trail that you might be able to tell if you were doing introspection. And that's really what it comes down to. Like some Sometimes you want to take an object and ask, well, what are you? You know, okay, you're a function, what's your name, what are your arguments? And so you lose all that information by wrapping it in this generic thing. So there's a standard module that will just say, this function that I'm defining is a function decorator. Please clean up all of its stuff so that it looks as much like the original as possible.
Understand? Where are you redefining print?
So the redefining, say hello. This syntax is what's redefining say hello. So this is identical to saying say hello equals show enter and exit, open parentheses, say hello, close parentheses. I'm passing say hello into this function and then redefining it as a result.
There where you say hello, you're just saying print hello. Where do you redefine print? I don't get it.
Oh, okay, not redefining print. I'm changing the behavior of say hello. So here the code that's actually getting executed is I'm calling what I think is a function called say hello, but this code up here gets executed because of the fact that I wrapped the function. It's syntactical sugar for just a way of modifying what a function does or behaves on its entering and exiting.
Does this drive you crazy when you're reading code and you think it's something but it's been wrapped?
I like it. I like this better than having some random place further down in the module that's redefined. Redefine it as this equals that. Like I like to have it up in the front to say this behavior has been changed in this standard way that I know of. So like one of the common ways in Django that something might be wrapped is that a view might be wrapped in such a way that all changes to the database are committed as a transaction or rolled back if something fails. Right? So that's a common way I would want a view function wrapped. Or I might say, this view can only get called by people that are authorized. So that concept is just a decorator that I can put on my view, and that's it. It's one line that I can add.
I'm just thinking for readability, wouldn't you want to use a different name rather than have two things that have the same name but behave differently? One thing
Maybe, I guess not if that's the only way that you're ever going to use it.
And if it's the only way you're going to use it, we can go back to the original function and rewrite it so it does that in the first place.
Oh, but you're reusing that same wrapping. The concept of this is a function that should only ever be accessed by an administrator, for example, is a function that wraps other functions. So it's a way of adding some extra common code to the beginning of something. All right? Good. Okay. Well, ask me afterwards. I'm happy to answer questions. So with I'm doing pretty well. So with the time that I have left, object-oriented stuff in Python, again, it's going to be different than a lot of languages that you're used to. Here is a simple here's a simple class. So let's have a look what's going on. Up in the definition, we define our base classes. I'm not going to deal with multiple inheritance today. That's too much of a mess. But object is something you have to declare in Python 2 as your base class. In Python 3, that's the default. This init function, which looks kind of like a constructor that you might be used to in other classes, has a strange property. Well, actually, all of these methods have a strange property that they've got this first argument called self, which is essentially this, but you have to put it there. And you have to explicitly specify it when you're assigning. So this is a line item. Each of these line items that I'm creating has a fruit and a price and a quantity that are set when I create them. But you'll see in the class, but the only thing that actually says that this object has these attributes is that they've been assigned in this code. So it's not the data types haven't been stuck in the class definition itself. So the object itself is sort of, you almost treat it like a dictionary. You can put almost whatever attribute you want, and just by the nature of giving it a name, it comes to be. It exists on that object. Actually, it's a lot like when you define a variable at a module level. It's the same sort of thing. Just by defining the variable, that name exists and you can use it.
So it's very similar to JavaScript,
Oh yeah. JavaScript is heavily influenced by Python, especially some of the newer changes. But yes, exactly. Like your objects are these, pincushions. You can stick whatever you want onto them. the common way of setting up default values is to require them in your constructor, essentially, your initializer here. So the next method is something that just operates on those, returns a total, sometimes quantity. That's fairly obvious. And then this is saying, if I want to turn this object into a string, say to print it, then this is a nicer way of printing it. Because we've seen some objects already that just say, foo object at random memory address with a couple greater plus signs around it. It's not very friendly. If you define one of these things, you can find a friendlier way to print your objects. Yes?
Since you're defining the members of that class just by those assignment statements at the end,
Yep.
can you add extra members later by just assigning more self-dot things?
By default, yes. So you can take some other object from somebody else and stick a value that you like to have on it, and pass it to yet somebody else. That's the default object model. It does allow you to do that. Internally, again by default, the objects that are created do essentially have a little dictionary of these identifiers where the values are stored. Each one of them does. So I just want to talk about some of that double underscore stuff. This is the stuff that's weird. This double under init, under, and the same with string. So this is Python's way of dealing with adding object-oriented functionality without adding syntax to the language. So all of the special stuff that goes on with objects in Python is defined by using these special method names. So if you need some of this special functionality, it's going to look for those names. And a reason that makes them so ugly with the underscores at the beginning and at the end is, for one, not to clash with anything that you might actually care about, that you might want to use. And two, to bring attention to it. You're saying, by saying that this is my init, and this is a special method, you should realize that it's not behaving like a regular one. But this is what lets you, at a fundamental level, create any types, any objects, anything that you want that behaves like any of the other stuff that I've shown you. You can make objects behave like functions, or like context managers, or like iterators. You can define special handling if attributes are missing. You can even nail down particular attributes that you want on functions. You sort of have complete control all through these special attributes.
If you overload the new print function, but you also overload the string method or some whatever, you lose that overloading if you don't take care to replace it?
No, you can still always access the built-ins by using the built-ins module if you want. Like you can say import built-ins, or from built-ins import print, and then you can have access to it. Of course, it is a dynamic language. You can also go into the built-ins module and do stuff like change the value to true and false, but don't do that. That would be crazy. So the code that actually uses it looks very similar. It looks like this. So you notice, creating it, I'm essentially calling the class name like it's a function. The values that I pass into that function end up on the initializer to store values into this object. And I access the attributes with, again, that same dot notation. My object name dot the attribute, and I get back the things that the initializer put there for me. I call functions like functions, so again, just using dot. And I can also assign values to this, and like was asked earlier, I can assign whatever random values I want to this thing, and it'll stick on it. And so there's my print statement, and the default that print does when it's handed something is it tries to convert it to a string to be sent to be sent out, and so my string operator gets called. This is one way of creating a whole bunch of these at the same time. And this is a data structure that is one of those cases where indentation doesn't matter. So I'm inside a square bracket here. I've got a list of, I've got a list of three tuples with the values that I want to pass in. And I'm using that splat operator to basically spread those out across the parameter values in the opposite way of, if when I define a function, I could say I want all the values that way. So shorthand. So I'm creating 3 of those and show you that they did actually get created. I can loop over them and print them. And here I can actually, I can show you that I can sum all the values in there, and that does what you pretty much expect. Okay, so far. So this is where things get interesting. If you want to change the behavior of the way these things work. Okay, well now first, I was talking about some of the special behavior of these objects. There's tons of documentation about it. It's if you do want to get some of the special stuff, it's better to go into that documentation. But one of the commonly needed things is to add a behavior to the way attributes are accessed on an object. And there's a whole bunch of ways of doing that. There's a get attribute special method that you can define. And this will always be called anytime you access any attribute. So like, in this code up here, item.fruit, that would have called my method instead of looking for the attribute in the object. Even item.total would have called get attribute to get the total attribute instead of looking in the class for that function. So this is sort of the all-powerful, completely rewrite every attribute access function. The next step, if that's not there, is to actually look in the instance for a thing called that. If it's not there, look in the class, and then look in superclasses for the thing called whatever that name is. And the more commonly used is one called getAttr, which is the fallback. If it can't find the definition in one of these others, it will end up in this function to try to give you a value for it. Yes?
So with all of this processing, every time you call a function, is a very large overhead.
Yes. And this logic, and it gets worse in my next slide, is one of the biggest challenges to the people that are trying to make Python fast, because it's so dynamic. Anytime you do a simple attribute access, depending on the complexity of this object, how it's defined, you could go all over the map looking up things that might be required to override in certain situations. The tracing JIT in PyPy does do a nice job of that because, well, it ends up being just one way for a particular object, and then all of that can just be collapsed into no code at all. But yes, that's one of the things that could make it slow.
Can you get the name of the attribute?
Yeah,
For example, that in that class you do have 3 names, and I don't know the names.
Right.
But I like to.
Oh, like just introspection. So if you have an object and you want to know what names are actually there. Yes, you can find out what names are defined there. There's a few different ways of doing that, looking on the instance itself. But yes, there are ways of doing that. So that's the more common way of changing the way this behaves. And there's also set attribute and delete attributes, so you can have special behavior that happens when somebody assigns to something, like if you want to limit what you can assign to, or if you want to limit the types or something like that. And then if that's not there, it actually goes and does it. People coming from the whole world demanded all sorts of fancy features in Python's object-oriented structure. So they did something interesting. Instead of adding syntax for all of this stuff that only object-oriented programming people care about, they created something called a descriptor protocol. I'll show in my next slide. But what it can do is actually take care of all this. The concept of, I've got a method on my class that I can call as a method on my class, and it doesn't have an instance. So it actually takes a class as the first parameter instead of self. Or a static method. It's a function in my class, but there's no self. It should be it just wants to use that namespace. It just, my special class dot whatever. And then properties are another really common thing. Notice there were no getters and setters. The default was you just stick an attribute on an object and you start using it. You can assign values or revalues. Usually the next step from there, after you've created an interface like that, where you've got direct access to this attribute to be able to read and write from it, when you realize that you do actually need to control that, the next thing you reach for is a property, which lets you define a function to call when somebody asks to get the value of this attribute, or set the value of this attribute, or delete the value of this attribute. So this is, again, a simple thing you'll see all the time, but these things don't really exist in the language. These are actually created with the descriptor protocol. This is my last real slide. And I'm going to have to try my best to explain what's going on here. So bear with me. You can define a descriptor, which is a class, which has a get, set, and delete, get and or set and delete methods. And when that exists as part of another class, those methods will get called when accessing that attribute with a whole bunch of stuff that you wouldn't normally get. You get passed to this function the owner, which is the class that the attribute existed in. You get the instance, if there is an instance, that it was accessed through in the case of get. And then you have the option of what to actually do at that point. And similarly, there's set and delete functions.
So would you say that Python has a full reflection, like in Java style?
Oh, yeah, you definitely got full reflection. And you've got, with this actually implements sort of that, the magic, the behavior where methods have self at the beginning, and it sort of seems to automatically get populated. Like when back here, when we call the total function, or in any of these things, I'm not passing self in here, right? So what's actually happening? This is how that happens. And this is an example of that. So essentially, a function is a descriptor. And this is a simple descriptor example. Here, you'll notice I am assigning to a value that is right in the class. Remember in my last class, I was assigning to values that were on the instance inside my init method. This is defining B that is part of class A. It's a new instance of my descriptor that has a get method. And in my code, I'm going to create one of these A objects, and then I'm going to access B through the instance. And when I do that, my get function gets called, and that function gets to see, well, the descriptor object that I created, also the original A object, and the original class that it was part of. On the last line here, I'm calling that same attribute through the class itself, and the only difference is that I don't have an instance. So the magic of sort of being able to support, well, magic, the ability to support all of these features that old will demand and absolutely must have, the class methods and the carrying objects on and stuff, is implemented with something that I think is pretty elegant fundamentally, and you can actually use this, though not many people do, to do whatever you want with these things. So they come up with a model that is actually really, really flexible at a fundamental level. So that's it. Yes?
So the way Python 3 is evolving, how would you say its strengths and weaknesses versus its competitors such as Perl and PHP?
The weaknesses are certainly just in adoption and in the third-party libraries, because it's a large effort to make the switch or to support the codes that it works across both versions. I've done it with the library that I wrote, which is a lot smaller than ones that a lot of people rely on. So you need to have a concerted effort by the developers, and not all of the major libraries are there yet, so lots of people are just stuck using Python too. Strengths are mainly that it's been able to clean up those things that really didn't fit or led people down the wrong path, caused lots of problems for people. By and large, they've done a good job of cleaning that up. Of course, I don't know what we're going to do with the next set of things that we realize we did wrong. Right? But there's been a promise that it's never going to happen again. there's a major shift like this, but we'll see. And I think the estimate of 5 years is probably reasonable, looking at how far a lot of major packages have come, as to the point when you can start to consider actually using Python 3 for a lot of the day-to-day stuff.
I don't know if for a user, but let's say, what is the advantage of using Python instead of Tcl or Perl or PHP?
Oh, I don't know if I can feel that one. I need to know the other languages better, and that can also get into a bit of a flame war. But I would say use whatever's got the community around it that you need. If the libraries that you need to use are there in Perl or in Tcl, and you have people that know how to use it, you can use it. but there are very large established libraries on the Python side, and it's a very pleasant language to work in once you get used to it. It's something that's pretty easy to pick up. The stuff that I was showing today was intentionally advanced because I didn't want to bore anybody, but it's not stuff you deal with every day. The everyday stuff is very easy, and would put everybody in a certain state problem. Yes.
Just something about porting to Python 3. I mean, I made the same mistake that I tried installing Python 3 myself and quickly backed out when I realized none of our Python code was work with.
Right.
Are there techniques to actually have Python run on both compilers or people or both interpreters, or do people actually have to re-implement it for Python 3?
There's two things you can look at. One is a project called Talks, which is designed to really help you with having your code run across Python versions. What I did in my case was I just started to use the tools that were provided. So the tool that converts almost all of the Python 2 stuff to Python 3, and then started running tests. And as stuff broke, I fixed things. It's quite possible to maintain code the Python 2 code, especially if you're only supporting later versions of Python 2, that will translate cleanly with those automated tools over to Python 3. But yeah, the main sticking point is just in what libraries you need to use. Like you said, you tried to use Python 3 and then you couldn't use any of your
stuff like that. You would have to convert the whole thing to Python 3. And
yeah, well, so it's internal code, right? You're talking about?
Oh yeah.
Yeah. So, is there really a need? I don't know. Like it's a significant effort to change.
Yeah,
Python 2 isn't about to go away. So you probably have to really look at whether it's worth converting in-house code to use a new interpreter, because there aren't in terms of functionality, you don't gain a lot. You'll get the latest GWiz features, with the interpreter, which makes some programmers happy, but it doesn't actually make any more money.
Yeah. So you're probably end up maintaining two streams if you do have a library, you be involved. But
it's possible to maintain one code base that will work on both.
So what you have
to change the way
you have a library that has like the print function, all that will work on Python 2 that you can.
Well, yes. So there are those tools, and basically you have to set up your Python 2 code so that it will work on Python 2, but that it will also act as a good input to those tools for generating code that works on Python 3.
Yeah, so just make sure that it converts.
And there are also tools that go the other way. I've heard you can write Python 3 code and convert back. Okay. But again, it's nothing sophisticated. Like the sort of analysis that would be needed in order to accurately convert the stuff, unfortunately, just doesn't exist. So it's still pretty painful right now. It's mostly just a bunch of regular expression conversions. So there's a lot of stuff that doesn't pick up.
Okay, thanks.
You could try out the specific things, right? Run one of those conversions, then add a from future import, blah blah blah. Try it.
Yeah, there's lots of strategies. I don't really like the from future import, using that too much. For those of you that don't know, you can change the whole behavior of how your Python 2 interpreter treats the whole rest of the code in your by using one of these statements. So I don't like that because you end up dealing with two different Pythons. If you take some code and move it from one file to another, it stops working because it doesn't have the right from future thing. So I'd say you have to use that sparingly. I tried to use methods that avoided pulling in specific features from Python 3. I just wrote my stuff in a way that with the help of that 2 to 3 converter would end up with working code.
No, I just went to migrate.
Yes, that's definitely one of the stepping stones and what that's there for. So you can pick certain individual features like the print function if you like it, or what have you that you can pull in. All right. Okay, thank you very much. As far as the code that's actually executed, the for statement here is essentially the first one. And what this does is it's calling a function. Sorry, the first thing that happens is that the Fibonacci generator is created. So Fibonacci, open parentheses, close parentheses. Oh, thank you. Technology. Fibonacci, the result of that is a generator object. operates on the generator capacity. So this is a new generator object that will give me x times 2 for each x that it gets out of the generator capacity.
Why does that need to be a sequence?
Well, SEQ is an arbitrary name because it'll work on any sequence type.
Okay, but so is it actually taking a sequence or is it taking a single value?
It's taking an object that it's able to ask for individual items from. So treating an object as a sequence. So this would work with a list, for example. Maybe I shouldn't. That's a confusing issue.
That's good. That's going to sound horrible, but that looks like a really high correlation, so please be careful where you say.
Oh.
Thank you. Appreciate it.
No one basically takes a generator as input and gives you a generator as output.
It takes any sequence, which includes a generator, as input, and gives a generator because this is a generator here as its output.
Oh, right, because you don't need a generator there. It could be a list.
It could be a list. It could be anything to be looped over. And then that's it. That's the last time that we call Fibonacci. The last time that we call double limit. The rest of the code is just in a loop where each element in the loop is just getting pulled out of that generator that was returned from double limit. So at the top of the loop, I ask for the first item from this generator. It says, okay, I've got a loop over this thing, which is a generator, which goes up to the Fibonacci generator. Gets the first item, comes back out, multiplies it by 2, gives it back to me.
I guess the part that's confusing me is the Fibonacci generator outputs individual values one at a time.
Every generator outputs individual values.
Okay, but so why do we need a sequence when we're only actually dealing with one value at a time?
The name may be confusing. It's anything that can act like a sequence.
But I mean, like, do we have to loop over it because we're only taking one input value?
We could call next on it to get each value, but we still need a loop somewhere to get more than one value.
Okay, but we're calling the object multiple times in the for loop.
We're asking for one item each time through the for loop. So internally, that's calling next, right? So that calls next on this, right? Which ends up feeding it through. So we end up with these 2 stack frames that are still active and partway through processing. And one drives the next to get the next value, and so on.
Well, correct me if I'm wrong, but objects that can be looped over have a generator inside, right?
No, generator is a special type of so sequences. A sequence is the general way of describing something that you can loop over. I think I'm not getting that wrong. And so a list is a sequence. A dictionary can be treated as a sequence. You just get it in a random order. Lots of collection types can be treated as a sequence. A generator is a very limited one that you can only ask for the next type.
They have some function like that inside that you can overload with one of these. I think I read that somewhere.
Fundamentally, they can be implemented as objects which have special method names that are what's getting called that actually makes this all work. This is sort of the using the language features way of doing it. You can get the same effect by making a class that has sort of turn it inside out, make a class that has methods that you can call. Is that what you mean?
You could define a new style of object, and if you want to make it a kind of object that can be iterated,
yes.
Then you define special methods. And
exactly. So the special methods that you need in that case is only underscore next underscore. So any object that has one of those can be treated like a sequence in this way and looped over.
Including a regular sequence, you could overload.
Well, the regular sequence comes with them.
Yeah.
All the regular
you can
sequences
overload it by using the special.
You can change them if you wanted to, yeah. Like that's not maybe something that's done in the case of like an order dictionary type. So dictionaries, you usually get all the keys back in whatever hash order that they come in. But a lot of people want to remember the order that things got inserted in, so that would be one way of doing it.
You can actually do much weirder stuff like we were developing something where time is discrete.
Yeah.
So you're thinking all over the place. You're thinking of a function that takes you from one instant to the next. You can implement it like that.
Absolutely. Yeah. And I use it. Sometimes I need to consume these things individually, and that case, like I might use the lower level, like calling next on individual items, and I do treat things where I just need to treat, you might as well use what's defined in the language, because then you can use instructions that are there. You can just loop over it for loop, or you can treat it the way you want. There's actually, if you like functional stuff, the func tools module has a whole ton of, all implemented in C, common functional stuff, like things that will work on iterators, but call operators in C so they'll be fast, to combine them, to zip them, or to, it's not doing justice, but if you like that style of programming, there's a whole bunch of tools for you there to look at.
So, I don't speak object-oriented, but I'm just wondering, why doesn't that say return seek times 2 in parentheses instead of for x is seek? Why doesn't seek replace x with seek? SEQ. Return seek times 2, that's it. Why does it say for x in seek?
Oh, because multiplying, so if sequence was a list, multiplying a list means actually taking its contents and doubling, so that already means something else. So it doesn't mean apply it to each item of. Like the way of saying in Python, I want to apply something to every item of something else is with one of these, with for.
But double it only needs one item for Fibonacci when that generator only needs, every time it's used only needs one item. Why doesn't it if we replace this instead of saying return x times 2, instead return Fibonacci in parentheses times 2? What would it do?
Well, you'd be multiplying the generator, which doesn't have anything. You'd get an error. You could ask it for the first off, you could say next, you could create this generator, say next on it, get one item.
So and then next Fibonacci times 2.
Yeah, and then you return that. So then double it would be just returning an integer, right? And an integer is not something that you can loop over, so this loop would give an error.
So even though it's in parentheses as a generator, it's still considered like parentheses Fibonacci times 2 open, or sorry, parentheses next Fibonacci times 2 parentheses as a generator.
Well, that's the thing that makes it a generator is the for in. Oh, sorry, the thing that makes it a generator expression is the for in. If you're making a generator function, it's the yield statement that makes it a generator function.
This is like
It's just shorthand.
in mathematics notation. That's where they took it from, where you define a set by saying take the elements in some of the set and operate on them like this, and whatever you get. Right.
Yes, Python is heavily influenced by the mathematics community. That's probably one of the reasons that 1 divided by 2 is now equal to 0.5. It was the main reason given. Well, you notice that imaginary numbers are in the basic language, and also it was the main reason given for Python not being case insensitive, because people who do math use different case letters to mean different things. But yes, they borrow heavily from that. They borrow heavily from all over the place. They kind of go halfway into a whole bunch of different paradigms from a bunch of other languages, but not so far to be completely consumed with their way of thinking. Is that right?
So a generator expression has to be something you can ask for multiple values from. Is that the idea?
It's shorthand for an object that you can ask multiple values.
So that's why you need the 4x in there.
Yeah.
Basically, you can think of it as something that you can loop over.
So even though Fibonacci is itself something that you can ask multiple values from, putting Fibonacci into an expression doesn't make that expression something you can ask multiple values from.
Exactly. It's just an object. It's just another thing.
You still need the 4x to make that happen.
How do you distinguish if you put the parentheses? Aren't you evaluating over Fibonacci?
So the weird, it's slightly subtle syntax. It looks kind of like a function, but it's not a function because it's got a yield in it. And the result of that is that calling the function is what actually creates the generator. Because you got to remember, each of these things has a call stack, so it's partway through. It has all its own local variables. So the act of calling this function is what creates one of those for you. Right? So if you took that and passed it to somebody else, it would still have the same state that it had the last time you were playing with it. But if you called this thing again, you would get a new one with its own local variables and its own local state.
But what I'm asking is, can you refer to Fibonacci without the parentheses?
Well, in that case, you're just referring to, I guess it's a function. Oh, I can't copy that.
And the point of my question is kind of because
Restructured text is a bit like pandoc, is that right?
A bit like what?
Pandoc form?
I don't know. Okay.
Looks like.
Yes, it's a function. So it is a function that returns a generator.
it's a function. Oh,
Yeah. To me, it looks like yield is a return, except for instead of returning a value, it's returning the state of the function until that point.
No, the state stays in the object.
Well, sure, but it's preserving the state and returning something that contains the state.
No, it's only returning what's on the side of the yield. So in this case, it's just returning an integer.
It's not returning the integer.
Oh, sorry, not returning.
The first time around, it's not returning the integer. This that function that you just pasted in there, it could say that the first time it's called with a global variable check, the first time it's called, it could return 1, and then the subsequent time, it could return a generator. Right? So it's not that the parser looks at it and finds the yield.
Functions only, I mean, technically they only ever return one thing, but that thing might be a
Well,
different
I could write such a function. The first time returned 1, and the second time it had a yield in its code path.
Oh.
And at which point it returns a generator.
No, any function that has a yield in it makes the whole function a generator function.
Sure.
Yes.
Can you do it?
What do you want to put in a return before?
As the first line, do if true, return 1.
Sure.
And then call it and see what it returns.
If true, well, oh, sorry, just return 1.
So the code, the text itself will still have yield in it, but it will never be reached.
Something like that.
I'm sorry, I can't see this.
Oh.
Yeah, it's the light on the left-hand side of the screen that.
Oh. All right. So it's something wrong there. Return. Oh, okay. So if you're not allowed to do if you return anything that conflicts with it being generated.
so you can just return.
And based on parameters, basically passed into the function, so it wouldn't know.
The parser picks that keyword out and makes it determination.
Right. Okay. So you can have a return in the yield at the same time.
And well, return. You can have a return that returns nothing. What that means is the generator's done. But you still get a generator back.
What happens if you're calling this thing and you come to the return, but you're expecting a value, so
You get a stop iteration exception. So you can. So if you're in a for loop, that results in ending the for loop. Right? If the expression is on the right side of the for loop, then that means the for loop ends. But if you're just calling next on it, then you have to handle that stop iteration exception and do something else. Okay, as I should probably clear it. Next topic. But we'll talk outside.